Howdy, welcome to the MXET 375 Summer Session 1 final project. I'm Harshit Kum and I'm working with Kevin Garcia and Quinton Bowling. We're part of Section 100 Group 3 and our project is the triple pendulum.
Howdy, my name is Kevin Garcia and I'm going to talk about the links here. So once this video is finished, we're going to upload it to YouTube and link it right here. And then this link right here is going to be for the team folder where the project is in progress, and you will be able to see the files. And it's already open for everyone with the link.
Yeah, so a little bit about our project. It's an open loop system 3-bar pendulum. So the whole project, the concept is detailed right here in this rough drawing, which is a frame built out of 80-20 aluminum extrusions, a 3D printed mount that's situated at the very top, and 3 bars that are 3D printed. All 3 of these bars are found on Thingiverse, which is a website that hosts CAD models for people to use in their projects. It's completely public domain, so everyone has the rights to use them. And we essentially 3D printed these at a makerspace and have these bearings force fit into each of the slots, including the bearing that attaches this top rod into the 3D printed mount that's on the aluminum extrusion. Now, getting over here, this is our prototype that we've built. So, as mentioned before, the frame is built out of 80-20 aluminum extrusions and essentially holds the basis for this pendulum to swing. Now, it's also secured by these 2 individual 5-pound weights. Those are just there in order to make sure that the system's stable. Given that it swings a lot, there's a chance for it to flail around. So the 5-pound weights are just there to stabilize the entire frame. And these are the 3D printed arms. They will be held up like this in a position similar to this, and they'll be let go, and the positions of each of these individual bar joints will be measured as a function over time. Now, when I let this go, you can see the motion of the pendulum itself over time, and there's individual stickers at each of these bearing joints. The primary method that we're going to use to track the pendulum is through a computer vision program, primarily written in Python and using the OpenCV library. It'll essentially apply mask and track each of these individual stickers by kind of ignoring the rest of the video and just focusing on the pixels that have these specific colors. And using that, we will essentially get the angular positions of the pendulum over time. And the objective is to find the friction coefficient of the bearings, which we modeled as damping coefficients. So we'll get the experimental data and use parameter estimation to try to fine-tune those individual damping coefficients.
Howdy, I'm Quinton, and I will talk to you about the plan of execution for our project. For our simulation, first off, we needed to simulate this in Simulink Simscape, creating the triple pendulum model. Once we got the model together, we started adding parameter variables for each of the bearings for its damping coefficient. Next, we ran it. We also used, well, actually, I guess before we ran it, we put in all the dimensions for the bars, which are approximately 17.8 centimeters long. And from the center of each bearing to the end of the rod is approximately 2.3 centimeters. So after all of that data was put in, so we have our revolute joints in the right position and our friction coefficients, we initially put in as a very small number, but they were attached to a variable so they can be changed with parameter estimation. Once we had all that in, we connected everything with Simulink Simscape and gathered the data from the simulation. We're hoping that whenever we compare it, well actually, that it will look like the prototype looks. We'll compare it to the experimental, and once that's done, we will run parameter estimation to hopefully fine-tune the damping coefficients in each of the joints. After we have the parameter estimation, we'll run it again and gather new data, and hopefully that one matches closer and it's more in tune with the prototype. For the mechanical side, we needed to plan the prototype, so we needed to find the dimensions, get ideas for how we're going to build things, choose the parts we needed, which came from Thingiverse, and then put everything together. The extrusions we got from Professor Garib in the lab, which thank you, Professor Garib. We got the bearings from a skate shop, they're just regular skate bearings. The 3D printed mountain joint did come from Thingiverse, and we printed them out of Makerspace. Put it all together, and that is prototype.
Okay, so here's the distribution of work chart. As you can see here, Quino was in charge of the simulation, which we already have ready. He was also in charge of the prototype building. I was in charge of prototype building too. So we both built the physical system. Quinton also helped with the equations of emotion, which I am leading right here. And we all are in charge of writing the lab report together. So we're actually gonna start doing the equations of motion tomorrow. And so Quinton is gonna be helping me with that. And then Harshit is in charge of the physical data. I'm programming to track the pendulum motion. And he's also in charge of the parameter estimation and of the model refinement, and he's also writing the report with us.
So the timeline, as of this assignment, the timeline, we're already halfway through it. We actually got it on the 19th, I believe. So we have a lot of this already done. We have our dimensions, we have our materials gathered. We haven't actually officially got the equation of motion finished yet, but we are going to be finishing that up tomorrow. The prototype is finished. The physical data collection is not finished yet. We're still working on tweaking the CV. The simulation building is built, but we don't have it completely complete yet. The changes will be coming soon also once we have the physical data done. The parameter estimation we will finish as soon as we get the physical data that we feel is the nicest, and then we will finally write our lab report. For our expected outcomes, we want the simulation initially to show the chaotic motion of a pendulum that we expect. We want our equation of motion for the tropical pendulum to make sense. And we want our experimental data that we pull from the prototype to be in a CSV file that we can use to have parameter estimation work, which means we'll have to adjust some values or shift the graphs. We want our initial simulation to at least resemble the experimental data. We want running the experiment or the parameter estimation to fine-tune the simulation to make it resemble and hopefully follow the prototype more closely for a longer period of time, because it is chaotic. It's not going to match perfectly, but we want it to match as closely as possible for as long as possible. Thank you. Or it should be awesome.